Okay, the exam's a little bit heavy on models, but it's just the nature of the course and the semester and the need to construct a test that makes you think a little bit. So you've seen almost everything I'm going to do here, but let's just kind of give it a summary. And of course there's another video that's about twice as long as this one, and you can watch me fumble through the whole thing. Okay, if you got a y versus t set of data, or y versus x, doesn't matter, you can draw a y versus x or y versus t. You can draw the data points. That's these little dots here. So they're a bunch of data points, they're a bunch of little dots. Now maybe you think a straight line fits those dots well. Well, you can draw that straight line, and you can estimate its y-intercept and its slope. You just take 2 points on the graph and figure out the slope. You could take 2 points on the graph, you could plug them into the form y equals mx plus b and get 2 simultaneous equations and solve them for m and b. There's several ways you can get the equation of that straight line. Okay, so if it's linear, it's pretty straightforward. Probably the easiest thing is just pick 2 points in the line, use them to get your slope and get your y-intercept, so that you have your slope and your y-intercept, and there you have your function. Okay, if the graph is curved, then it's not linear, it's not a straight line. So maybe the curved line is exponential, maybe it's a power function, maybe it's a quadratic function. Exponential function for y versus t would be y equals ab to the t. Or alternatively, y equals ae to the kt. In both cases, you have 2 parameters. You have a and b here. Okay. Here you have a and k. If you take 2 points on this graph, let's say that this point here and this point here, take 2 points on the graph, you can plug them in to this form. So you take the point -1, 3, plug in 3 for y, -1 for t, you get 3 equals a times b to the -1. Plug in 5 for y, 6 for t, you get 5 equals a times b to the 6th. That's a system of 2 simultaneous equations that you can easily solve for a and b. Your strategy would probably be solve the first equation for a and then plug that expression in for a in the second. You get an equation in b, and it's a simple equation to solve. Okay, if you have this form, and this is equally valid, and depending on whether you're asked to do one form or another, you might use this one or you might have your choice. You've got to plug in, again, -1 for t, 3 for x, 3 for y, and here's your 3, here's your -1 for y and t. And same thing for the point 5, 6, y is 5, x is 6. You get this equation. There's a system of 2 equations. Again, you can solve it. In this case, the k that you're going to solve for is in the exponent. You're going to have to use a logarithm, but you know how to do that. Okay, so we have these 2 equations. Now, you can do a power function model as well. Power functions just like ax to the p or at to the p. The variable is now the base, as opposed to an exponential where the variable is up in the exponent. Okay, this is like ax squared or ax to the -2 or ax cubed, whatever. Okay, we have this form, and using these points, we get 3 equals a times -1 to the p, because of course -1 is your x value or your t value, it goes here. The p is a parameter. We don't have a p on the graph. Okay, we don't have a p in the data. So a and p are things you got to solve for. Okay, so we've got 3 equals a times -1 to the p, and from the point 6, 5, you're going to get 5 equals a times 6 to the p. Again, you can solve for a, plug it in here, and then solve for p. Again, you have to use logarithms to do the solution. Okay, it's a quadratic model. Well, that's pretty straightforward. You need 3 points. Because you have an a, a b, and a c, you know that you need 3 simultaneous equations to solve for 3 parameters. Okay, got to solve for A, B, and C. So we get a third point here. We plug -1, 3 in, -1 for y, 3 for y, -1 for t. We get this equation. 2 for t and 4 for y. We get the 2 for t and the 4 for y. 6 for t, 5 for y. 6 here, 5 here. Gives us 3 equations. We do the arithmetic. We square -1, 2, and 6, and we get these 3 equations. And now we can solve those equations. Just if you subtract any equation from any other equation, you're going to eliminate C. You do that for 2 pairs of equations, and you're going to get 2 equations and 2 unknowns, and that gets a lot easier. So then you solve those and you back substitute. Well, you know how to do that. Okay. Another way. You got y versus t data, and this way works if you have exponential or power function data. It won't work for linear function. It won't work for a quadratic function, but it will work if your data is basically exponential or quadratic. Exponential or power function, sorry. You got your data, so you make up a table. Okay, here's your y versus t. Y goes here, t goes here. Log y versus t. Log y goes here, t goes here. But don't reverse it. Don't put log y here and t here. Even though, since it says log y versus t, you naturally want to write log y here and t here. But log y versus t, log y goes here, t goes here. Y versus x. The y goes here, the x goes here. Okay? Okay, so you got log y versus t, and to get log y versus t, you just take your y values and calculate their logs. They go in this column. If we want to do log y versus log t, you calculate the logs of your y values, you calculate the logs of your t values, and you put them here. Now, you graph. Whatever you get here, you graph versus t, and you get a graph. If it's a straight line, or suggests a straight line, you figure out what that straight line ought to be, either estimate it graphically or use regression, and you're going to get a slope and a y-intercept. Okay? Now, if I've got a graph drawn on paper, I can take 2 points, get the run and the rise, divide the rise by the run to get the slope, and I can see where the graph crosses the vertical axis. Then I know that I've got something like a y equals mx plus b, but in this case it's not y versus x or y versus t, it's log y versus t, so it's log y equals mt plus b in this case. Just like y equals mx plus b, but it's not y, it's log y, and it's not x, it's t. Over here, okay, this one might not turn out to be linear, okay? If it isn't, well then maybe you try this one. Okay, if this one turns out to be linear, then you have a graph of log y versus log t, and the equation is log y equals m log t plus b. Again, it's like y equals mx plus b, but it's not y, it's log y, it's not x, it's log t. So it's log y equals m log t plus b. In either case, if one of these turns out to be linear, the other won't. They won't both be linear. But if one of these turns out to be linear, you're going to get an equation that's more or less valid that you can then solve for y. And I'm not going to go through how to solve for y here. I'll just, you do 10 to the log y equals 10 to the quantity m log t plus b, or 10 to the log y here equals 10 to the mt plus b. You convert the thing to exponential notation. In any case, one way or another, you solve the equation for y. And that's another method for getting an exponential or a power function fit to your data. Now there's a longer version of this where I actually wrote things out. If you want to watch that, you can watch the longer version. If you understand this, then go ahead and apply it where it's necessary.